Hello and welcome to a presentation on Bernoulli equation. Your first question will be, what is the Bernoulli equation? This is a continuation of the work we presented on the first order linear equation, which we saw before. Like we know that a first order linear equation looks like this, or it is an equation can be reduced to this form. I hope you still remember what we said about P and Q and how you solve this equation, because if you don't remember and you haven't practiced enough to solve a linear equation, this is look like sort of something a bit strange. Remember, in the absence of knowledge or experience, anything is surprising. So I hope you're not going to be surprised by some of the things we're going to do in this section. So coming to what is a Bernoulli equation? A Bernoulli equation is an equation which can be reduced to look like this form. In this case, reduced in terms of manipulating it algebraically until it looks like this. Very important to notice that look at the left-hand side of the linear equation and that of what I'm calling here a Bernoulli equation is exactly the same. So what warrants us to name this equation differently is this vector we have here, y to the power k, and the k here is a real number. So immediately once we've got the experience of the linear equation and we've got this equation, we can now proceed to look at how exactly we can solve this equation, of course exploiting our experience on solving the first order linear equation. So now turning to solving or integrating the Bernoulli equation, we are, for now what I'm going to do, I'm going to sort of present you with a roadmap which we're supposed to follow in order to solve this equation. So first of all, let's say our roadmap is as follows. First of all, we're going to need a helping variable to solve this equation. So what our initial step will be to let u be equals to y to the power 1 minus k. So u here is going to be our helping variable, and since y is a function of x, like is shown here, dy dx, so u is actually a function of x. So what we're going to do now, we're going to differentiate u in terms of x. Using power rule here, we're going to say du dx is equal to 1 minus k multiplied by y to the power 1 minus k minus 1, which will simply be minus k multiplied by dy dx as the argument of the power function here. And that will be the derivative. So if you note now, the dy dx here appears here in the differential equation. So the only factor which is not there in the differential equation is this one. So what we're going to do, we're going to take this factor and multiply the whole equation throughout left and right. So that's our second step now. So multiplying there, which basically copying this term, it will be 1 minus k multiplied by y to the power minus k dy dx plus multiplying this term, the second term there, we're multiplied by this underlined term here, which will give us 1 minus k times p x. Notice that this yk, you can put it next to y to the power minus k, you can put it next to the yk here, y to the power 1 here, which will give us y to the power 1 minus k. Notice that you put y to the power k here, multiplied by y to the power minus k. Using exponent rules, you're going to get 1 plus minus k, which is 1 minus k. So that's what we get at the end. Then equals on the the left hand side, on the right hand side, multiplying there, we will be multiplying by this. In this case, now we're going to multiply y, k, multiply by y to the power minus k right here, which will give you y to the power 0, which is definitely yk divided by yk, which is 1. So we're going to be left here with 1 minus k multiplied by q of x. I think at this stage we can sort of become comfortable saying this is a linear equation. Why am I saying that? Check. This is u, which is this part. So we can write this part here as 1 minus k, which is a constant, multiplied by p of x multiplied by u equals to 1 minus k multiplied by q of x. And then this is what we call here du dx. du dx. So now if you look at this equation now, it has got a structure of a linear equation. So in our first presentation with the dy dx, here we got du dx, and now we've got this part here representing our original p of x in the original standard form of equation dy dx plus px y equals to q, because this is just a constant that doesn't make any difference there. Then this is a linear equation, but now the unknown here is u. So we first of all go to solve here for u. So once you have solved for u, we can now substitute in this equation here and now find what, be able to find an expression in terms of y as a solution. Of course, this is the kind of overall idea of what you are expected to do, taking into account all these calculations. So now I think the best thing to do is to look at an example, which is in this case our point number 2 is our point number 2 will basically, after finding u, substituting and finding a solution y in terms of x. That's what we will do. So looking at an example, let's look at an example like this. I decided here to choose example with the initial conditions so that we can actually practice two things at the same time. Let's start with this problem. So let's say solution. Now we look at this equation here. We, like before, we have got to identify our p. Our p in this case looks like is a constant 2, and our q is a constant 1, and then we've got y, k is equal to 2. So what we're going to see here, step number 1, let's note that k is equals to 2. So then let our u be equals to 1 to the power 1 minus 2, which will simply give us y to the power minus 1. Then doing the differentiation to du dx, which will be minus 1 y to the power minus 2 multiplied by dy dx. Then our next step will be to multiply the whole equation by this factor here. Then if we do that, we're going to have minus 2, sorry, not minus 2. If you multiply by this factor on both sides, we're going to have minus 1 y to the power minus 2 dy dx plus minus 2 y to the power 1 multiplied by y to the power minus 2 equals to 1 for q times y to the power 2 times y to the power minus 2 with a minus sign there. Then let's draw a line here. You can see clearly that this is going to give us 1, and there we're going to be left with minus 1. And this is going to be u, so du dx. Then we've got here du dx plus minus 2 u, because here we've got y to power 1 times y to power minus 2, which will give us y to power 1 minus 2 equals to y to power minus 1, which is our u. So we've got that equals to minus 1. So now, what the next step we're going to do now, we've got a linear equation, du dx p, which is minus 2, u equals to 1. So we can now identify our p, identify our r, then get our integration factor, resolving factor. So that will be our step number 3. So coming to step 3, we are now in the presence of a linear equation, du Now coming to our step number 3 here, we are now in the presence of a linear equation, which is du dx plus minus 2. I'm keeping this minus to sort of in brackets like that to maintain the standard form of the linear equation, multiplied by u equals to minus 1. So identifying our p here, our p of x is equal to a constant function minus 2. Our q of s is a constant function minus 1. Now we need our resolving factor. We need our resolving factor, and we said our resolving factor comes from p. So resolving factor r of x equals to, we said comes from p this way. It's e to the power integral of minus 2 dx. That will be our resolving factor. So integrating here, I think it's clear to everybody that this is going to be e to the power minus 2x, and we don't need to add a c here, even if this is a indefinite integral. So now we've got our integration factor. Now presenting the solution. Now remembering what we said about the solution of this equation, now that will be step number 4. We said once we've got a integration factor, we can say y, in that case, the role of y is played by u, multiplied by the integration factor will be equals to the integral of q multiplied by the integration factor. So doing that here, we simply say u multiplied by e to the power of minus 2x equals to the integral of 1, that is for q, multiplied by e to the power minus 2x dx. I suppose you've done your revision of integration of all the types of functions, including exponential functions. Then here, our integral will be e to the power minus 2x divided by minus 2 plus c. Then we are ready to make use of this formula by dividing both sides by e to the power minus 2x. And doing that, you get u of x equals to minus half, dividing here by that, you get 1 plus c e to the power 2x. And according to what we saw before, we said u was equals to y to the power minus 2. Which you can write simply as 1 over y squared. Now we can forget about u and just focus on the equation which comes up from there and there. So simplifying this, we will simply have y squared equals to 1 over minus 0,5 plus c e to the power 2x. I hope you can see here what I did is I just inverted this, interchange the numerator denominator this side, and this side the denominator of this whole expression is 1. So I did that. So which will say now therefore y is equal to 1 over the square root of c e to the power 2x minus 0,5. So then this is our general solution. Just write ds there. But remember, we're given initial conditions. The conditions say the y at 0 is equals to 1. So now we can move on to find our particular solution. That is our step number 5. So what we do is y equal to 0 equal to 1 implies that 1 over square root of c e to the power 0, substituting x with 0 there, minus 0,5 is equal to 1. So notice that here now we've got an equation in terms of c. Our known here is c. So what we have here simple is 1 over the square root of c minus 0,5 equals to 1. And the squaring both sides here, we simply get 1 over c minus 0,5 equals to 1. Then we can solve this by multiplying both sides by the denominator, which will give us 1 equals to c minus 0, 5. Obviously, I hope you note that for this square root to be valid, c minus 0, 5 must be greater or equals to 0. So then, it means that we've got here that c is equals to 1 plus 0, 5, then which gives us 1, 5. Now writing the particular solution, we'll take this as y equals to 1 over square root of 1, 5 e to the power of 2x minus 0, 5. That will be our solution for this exercise. I hope that is clear. Now let's turn to the next example, and which will be the last one for this presentation. In this case, we've got the equation given there, the Bernoulli equation. Then starting on the solution, we have to do the same thing, identify our p. In this case, our p is x, and identify our q, which is also x, and our k in this case is minus 1. So starting again in a similar way, we'll then say let our helping variable u be equals to y to the power 1 minus k. In this case, k is minus 1, which will give us y to the power 2. Differentiating, get du dx equals to 2 y to the power 1 dy dx. So then we see that the common factor of both here is, the factor of both here, the new factor is both is this one, which we're going to multiply the whole equation with that. So what we're going to have here is going to be, let's say step number 2, we're going to have 2y dy dx plus x y times y, actually 2xy times y equals to x y to the power minus 1 times y to the power 1 with the 2 there. Then again, we notice that here this is y squared. Then we're going to have here 2x by y squared, and here we've got 2y dy dx equals to 2x times 1, because here we've got y to the power 0, so then this is 2x. So writing this in terms of u, we get our equation du dx plus 2x u equals to 2x. So then we've got our standard form of a linear equation. So now what we're going to do is the following. We're now going to do our third step, which is going to be identify your p of x, in this case, which is what, 2x, and then identify our q of x, which is likely again is 2x, and then we'll need our r, our resolving factor, Our solving factor is usually comes from P. Then we've got R of x, which is e to the power, the integral of P, which is 2x dx. Integrating this, we get here e to the power x squared. I hope I'm not too fast there. I'm expecting you to be very fluent in this kind of integration. So step number 4, we now know how our solution and integration factor interact. We said our solution, in this case u, multiplied by our integration factor, which is e to the power of x squared, would be equal to the integral of q, in this case, which is 2x, multiplied by the integration factor, which is x squared dx. Now, if we check what we've got here, let's take the function e to the power of x squared, and you differentiate that. You remember the derivative of exponential function is the exponential function itself multiplied by the derivative of argument, which in this case is going to be 2x, multiplied by the ln of the base. In this case, ln of base e is 1, so we've got here 2x e x squared. If you remember, definite integral simple asks for the function which differentiates to the function which is under integral sign. So this is a derivative, like we see, of e to the power of x power e to the power x squared. So the answer here will be simply e to the power x squared plus c. Now, what you can do is to now make use substitute formula by dividing both sides, which is going to be u of x equals to 1 plus c e to the power of x squared. And then we were told there the condition was saying this is our u now. Remember, we've started substituting y to the power y squared. So now we have arrived at u, which is 1 to plus c e to the power. So remember, this is equals to y squared, which is our u from the beginning. So then we can simply now say, therefore, y is equal to, so there's something strange here. This is supposed to be minus x squared, e to the power minus x squared, because we're dividing by this term here on both sides. Divided here to become 1, and then it comes here to be e to the power minus x squared. Not that, sorry for that mistake there. So then here we're going to have y being equals to the square root of 1 plus c e to the power minus x squared. That will be our general solution. Now, moving further on, for a particular solution, determining our particular solution, then we will use the condition we said y at 0 is equals to 2, which implies that evaluating this expression, 1 plus c e to the power 0 squared is equals to 2. So squaring both sides here, we simply get 1 plus c equals to 4, and therefore c is equals to 3. Now we can now write the solution as y equals to the square root of 1 plus c e to the power minus, sorry, I'm writing 1 plus c again here. That's not supposed to be. That would be 3 e to the power minus x squared. That is the function. And remember, when you find a particular solution, you must remember that this is a unique solution. In this case, it will be a unique solution which passes through the point 0, 2. That is about this condition given there. So this will be the only solution of that differential equation which passes through this point, which satisfies those conditions. So this marks the end of the second example. I hope you are getting familiar with how to proceed with this. Let's just see what happens from the first example. This was the roadmap which we sort of gave to solve the problem, but obviously at this stage it is not very, very clear what exactly we are supposed to do. But when we come to the example here, you should note exactly what kind of substitution you did until you get to a linear equation, and then solving your linear equation in terms of u using the integration factor. I hope that was clear. The integration factor of that, you multiply both sides, you integrate one side, you got this, and then you then find the expression of u. You do the right manipulation to find y as the substitute of the formula. Then you evaluate the conditions given to find your particular solution, which at the end you must give it as a solution at the end which you're supposed to do. You must show all your calculations that I'm doing here. I'm not saying my handwriting is beautiful, but I think my work is very, very clear from the beginning to the end. Then the next example, we did exactly the same thing with a different function, though they are both exponential function, but the process is exactly the same again until we get to the particular solution. I think at this stage now, the ball is in your court. You need to practice in order to master this and do it independently. Of course, during your practice, you can practice as a group, but you must target that at the end. As an individual, you can do the whole process of finding the solution to this type of equation. So, for you, you do the following examples, and as you can see, the order says reduce the following to linear and determine the general solution for each of the ODEs. In other words, this exercise, some of them have not much to change, like for example this one. But if you look at this one, you have to manipulate it first so that you leave q or y to the power k on one side and then do the rest substitution and proceed. Otherwise, at this stage, I would like to say thank you for listening. I hope all goes well with your practice.